Good afternoon, everyone. Welcome back. If you were here this morning, I'm sure you're like me, you're looking forward to this keynote and the following panel discussion. If you're just joining us, we have some good content for you. My name is Nate Chambers. I am an associate professor in computer science here at the Naval Academy. My research area is natural language understanding. So I'm particularly happy to introduce our keynote, who is an expert in natural language understanding. If you're not familiar with the area, it's the study of how we can get computers to understand human languages. English, Spanish, Chinese, me talking to you right now, can computers understand it? To me, this is one of the fundamental challenges of artificial intelligence. Language is messy, it's ambiguous, and yet it's core to the human experience. And so when we talk about building intelligent AI, language has to be the core piece to it. If you were here for the morning keynote, our speaker talked about how he got into AI when he first read a particular book. For me, it was actually a class I took as an undergraduate. It was a class called Natural Language Understanding, and it was that class when I was a junior as an undergrad that kicked me off doing what I'm doing now. So to all the midshipmen in the audience, first of all, thanks for coming. But yes, a class can change your life. So keep your minds open and look forward to what you can explore. Looking back, one of the first research projects I actually worked on was a dialogue agent. So this was about 20 years ago in the year 2000. Dialogue agents were really coming about. We built one for the elderly, and the goal was to get the elderly able to speak to a system and ask questions about their medication. It was a very clunky system, lots of sort of hand-coded rules, and yet, it was interesting to work on. Shortly after that, DARPA put a large amount of money behind a project called Kalo, and the goal of that was to build an intelligent conversational system, which could be an assistant to someone in an office setting, to the DoD out in the field. How do we build an intelligent system? This project was a 5-year, one of these massive $100+ million research projects. And in the end, the Stanford Research Institute at the time was sort of leading all the universities that were involved. And this institute is called SRI, if you're not familiar with it. Some of the researchers there actually spun off the idea of this intelligent system. And they made a startup company right when smartphones were coming about, and they wanted to make an app that you could ask questions to and get responses. And so they spun off from SRI, and so they couldn't call it that, so they added one letter, and they called it Siri, right? And so this is the system that Apple ended up buying to build Siri. Looking back at all this stuff, a lot of these systems were very much hand-built rules. The user says this, then I'm going to do this. And they were very brittle. Right? The interactions were difficult. If you wanted the user to just speak and go kind of freeballing it, right? Then it wouldn't work. It would break. And in the end, I actually found this to be too difficult, and I switched my research area into a different area of language understanding. And so this brings me all around to, it's my pleasure to introduce our speaker, because he clearly does not find this too difficult. And so our speaker is Prem Natarajan from Amazon. He is the vice president of their Alexa division, and he leads their natural language understanding unit. The natural understanding unit. They do more than just language. And Prem comes from a very rich background. He was the vice dean at the University of Southern California, and he was the director of the Information Sciences Institute right before he moved to Amazon a couple years ago. If you're not familiar with ISI, it's a world-renowned research institute doing AI. The number of researchers they have there is roughly equivalent to how many civilian PhDs we have here at the Naval Academy. So if you take all of the Naval Academy's civilians, that's ISI, all doing AI-type stuff, and Prem led this group. Before then, he was at BBN, and he led similarly sized groups in language understanding. He has a rich history of this and is now leading Alexa. I'm very excited about his talk. It's entitled AI in Our Lives Everywhere. And as a user of Alexa myself, I can attest that Alexa is everywhere in my house, which is both exciting and frightening. So I'm looking forward to it. Please join me in welcoming Prem Natarajan, Amazon Alexa.
Thanks. Thank you for that introduction, Nate. Let me, it's a good thing that I don't have to introduce myself, so let me just skip straight to the next slide and keep the momentum going. So I've put together a sort of a new narrative for this group. Starting from setting the context with the evolution. My talk is in 4 sections, sort of. The evolution of AI, what I think of now as the origin story of AI, some salient advances, and then a personal perspective on what I think is a transformational advance that has driven AI to where it is today. Then a look at a topic that's near and dear to my heart, conversational AI, in the context of human-computer interaction. And there we look at Alexa, some features of Alexa, some of the advances we've accomplished with Alexa, mostly as an example of how AI is having an impact in our lives everywhere. And then I'll conclude with a section going over the risks of AI, and of course, any topic like the risks and opportunities with AI is a broad one. So I've chosen a couple of examples to highlight both. And then I conclude with what I think we're doing in this area to make the change. Just to set context, sometimes people say, how is AI going to change our lives in 15 years or 20 years? Or what's AI going to be like? How broad is its impact going to be? AI is already at the center of our worlds in many ways. It's impacting nearly every part of our endeavors today. Whether it's the humanities, and you think of the digital humanities project and all of that, there's a lot of machine learning and stuff enabling the researchers in that area. Think about medicine, privacy and security, gaming experiences. All of these are AI-driven experiences today. So how did sort of all this happen? Where did it start? So I thought I'd start off with a bold, there are lots of bold statements in American technological history, and we're a fundamentally optimistic society, so these bold statements set out the vision for the future, and then we pursue those with a passion and rigor that's sort of unmatched in the world. So I'm now based in LA for the last 6 or 7 years, so I thought this was very apropos. I would start with one of the early workshops in this topic called the Session on Learning Machines. This was just 1 year before the phrase AI came into vogue. John McCarthy introduced it. So Willis Ware, who was the chair of the session, thought there was considerable promise that in the relatively near future, many types of human activity could be done by machines, like many types of things. That was 64 years ago, and it's one of those statements that's enduringly true. It is still true that many types of human activity can be achieved by machines in the relatively near future, though we've made a lot of progress in that sense. I started first assembling this slide saying, let me go over salient advances in AI and sort of give some context. And then I realized that I was not able to distill it down to just a few that fit in a slide in order to tell the story properly. So I have now 3 slides where I break them down into sort of 3 phases within this 70-plus year period. But the main takeaway from this slide is that this was a massive effort across the world over the last 70 years. And interest in AI has waxed and waned. So we should expect that it will wane again, but this is an endeavor that has lasted for a very long time, 70-plus years. The first AI winter, as some people like to call it, was from 74 to 80, when there was a lot of buildup of expectations and then a sense that it didn't meet our goals and a lack of funding and commercial interest. Then there was a surge again, and then a second AI winter, and then what I think of today as sort of the age of the perennial AI spring is what we're in. So from the 40s to the 50s, in the 40s and 50s, sort of the exciting new areas. All of these slides, there are 2 sections, top half and the bottom half. I've tried to sort of present the AI, general AI evolution, and then because natural language, as Nate pointed out, is a topic I care about, sort of salient milestones in there. A lot of early work in AI was driven by, the most obvious manifestation of human cognition is language. It's in how we sort of express ourselves, communicate with each other, et cetera. So it's not surprising that language is what drove a lot of early AI advances, though then things like motor control and moving and picking up and performing tasks all became of interest. The key point on this slide that I'd like to highlight is these three sessions. Up until that point, there was a fair amount of disparate activity, many different people doing things. Interestingly enough, machine translation was one of the earliest applications of AI, and it still is, we're still improving performance in that area. But those three sessions, starting in 55, 56, and 58, really started the formation of an aspirational AI community that said, we want to replicate certain parts of human cognition in machines and see if we can have machines do those tasks that we normally think require human intelligence. The other takeaway I'll say here is ARPA, which is now DARPA, was founded in 1958, and they've been a major, major force in the forward movement of AI in the decades since their formation. The 60s, the key observation on this slide you'll notice is the amount of practical application of what we think of as AI today. So this was in the 60s, right? In some sense, when we look back at history, it's still a formative field, but there was tremendous optimism. Can I, for example, do target detection in aerial photography? That's in 62. Can I do face recognition? That was in the 70s, actually 1970. Stanford student wrote this program first. It was very restricted, very controlled, but showed the promise of AI. And then I'll accelerate to this thing. The second part of this period was massive government investments across the world. Two examples of it: DARPA invested in the speech understanding program and the image understanding program. Japan invested in what was like a nearly $500 million program over 10 years at that time called fifth generation computer systems. They anticipated AI being the fifth industrial revolution or whatever, but fifth generation computer systems, all of that came to a crashing end by the end of the 80s. DARPA stopped its strategic computing initiative in 87. FGCS sort of wound up in the late 80s. That was sort of the second AI winter I was talking about. Then this thing from the 90s, the 2000s to 20, this is when I think we started finding our footing in terms of saying this is an enduring area. We have to be in this area as humans. We have to advance this area. There's tremendous potential here. And in this time, there are two developments that mark. The first time that we actually showed computers could perhaps be superhuman at some tasks. That was a major milestone, to just get it into our imagination, that computers can beat humans at something that looks like reasoning. And chess, in many ways, in many of our imaginations, is the pinnacle of human reasoning, though it turns out Go is much harder, which is why that happened in 2017. The other thing is all the launch of all these commercial capabilities with AI, starting with Dragon Dictate, which was a very sort of word-by-word kind of speech recognition dictation system. 97, they released Naturally Speaking, where you could just talk like I'm sort of talking now. I remember testing that product out. I was at BBN back then, and I was surprised at how well it worked as a product. You could give it commands and say, go back, delete the last 3 words, and it would do that. And you would go and say, spell that word. This is, it gets a word wrong, you highlight it and say, I actually meant John, John, and the next time it would recognize it. So all of that kinds of thing was starting to happen back then. And of course, 2 key advances in my mind. One is the invention of generative adversarial networks, which happened in 2014, and the launch of Alexa, which really was the creation of what we think of as ambient computing. You're no longer touching, feeling things, you're just talking to your environment. Your environment talks back to you. Right? So all of that, it has taken sort of the collective investments and endeavors of governments across the world, industries, the creativity of many individuals to get us to what we think of as the golden age of AI today. And it's there everywhere, from like self-driving cars, language, and of course, something I care about, conversational AI. So the question is there one transformation that that got us to this point. And it's always risky to answer a question like that with a yes, because it's such a subjective perspective on things. But because I'm sharing my perspective in this talk, let me sort of just be bold enough to say, I do think there was one transformative change that has enabled the AI revolution. And I think that's both the idea and the methodology of machine learning. Right? And let me tell you why. So first, we'll do a few slides that look somewhat technical, but really not. So data-driven machine learning, this notion that you can actually learn how humans perform tasks from data without humans writing explicit rules that tell you this is how it's done, in my mind, was a conceptual breakthrough. The fact that you just need lots of data to learn from. And then the methodology that made that conceptual breakthrough possible was machine learning. If you look at this slide here, the power of this methodology is that you have, looking at the bottom half, which is the training or the learning phase, all you need is the input is training data. And the training data is just, in the case of speech recognition, just speech signals, like I'm just talking now. And the answer is simply the sequence of words that I'm saying. Anybody with high school proficiency in the language can actually transcribe that speech and say, this is the sequence of words in this speech. That's all we need. We don't need humans to tell us this is where the word starts or ends, this is where a phoneme starts or ends, or that this is how we produce language, right? And the trainer learns something that we like to call model today. The model forms the sort of the brain or the network in our brain, if you will. It's a very loose analogy, just for purposes of explanation. Then you have this runtime thing. We call it a decoder. You can call it inference. In this case, all that comes in is the input, and the decoder or the inference engine takes in as the second input the model. That's like the human now. Together, these two. And it produces, and this particular formalism has been applied to area after area. Machine translation, computer vision. This, at the conceptual level, this formalism has held true for now maybe 4 decades, maybe slightly longer. Now, supervised machine learning, which is what I showed you in the previous one, which is basically you have the input. Some human has labeled the input with the answers that you seek the machine to give you, and then the machine learns from it. It's by far, even now, the most popular form of machine learning. The workflow goes somewhat like this. You have unlabeled data samples, that's like my speech. An annotator transcribes that speech or labels it in some way. The labeled data samples are then used for model training, and then you get this, right? This is just a workflow instantiation of the diagram I showed you in the previous one. And here's an example. So you have, on the bottom left, just the data, which is just, in this case, very simple, cats and dogs. An annotator has gone through and labeled them as either cats or dogs. The model has learned how to distinguish between cats and dogs. And then the inference engine reads in the model, takes in new test data, and predicts that it's a dog. Right? So this is sort of the core essence of what we think of as machine learning. There are many variants of it. How can you do it with less labeled data, that's less supervision? How can you do it with completely unsupervised data or completely unannotated data? How can your learning signal be a reinforcement signal as opposed to something that's provided a priori, et cetera? So many different flavors, but this is sort of the essence of this thing. So what's different? So we've had this for a long time. So what is different about deep learning? Why has deep learning launched this sort of revolution sort of in the last 7 years? One key difference that I think, at least in many of the fields that I work in, that it has helped with, is that before deep learning, we spent a huge amount of effort in what's called handcrafting features. Whether in the case of speech recognition, it was the Kepstrel coefficients. In the case of image processing or object recognition, it was SIFT features, histograms of gradients, et cetera, et cetera. We spent a huge amount of time saying, what are the features that best represent this thing that I'm trying to infer? and then we train the models, et cetera. With deep learning, the system automatically learns the features and the models jointly. What this does is it frees up the human from having to impose preconceived notions of what are the distinguishing aspects of anything. So for example, with image object recognition in images, you no longer need to put in like SIFT data or like SIFT features or histograms of gradients, et cetera. You just say, this is the input, this is the output, and the network learns, there's a part of the deep network that actually learns the representation, which you can cut the network at that point and output the representation if you want to use it for other tasks like visualization, et cetera, right? This, in my mind, is sort of the transformation in deep learning, that you can just do it end to end. Of course, the other big transformation is that it just works so well. It's just way superior. You saw that chart in one of the slides this morning, where you saw that the error rate improved from something like 25% on a task down to 16%. That kind of improvement is unimaginable without a technological shift. And that was a huge improvement, and that's why there was immediate movement to deep learning across many communities, because there were entire communities worried about their approaches and their work becoming irrelevant without jumping onto this bandwagon, because it was just so much better. So to summarize what we just saw on the AI technological evolution, and this is an important slide for some of the part that will come towards the end of the talk. There are 2 or 3 interesting things in my mind. One is that we went from handcrafted features to automatic features. Sort of these systems went from rule-based systems to Bayesian models, neural networks. These were shallow neural networks. These were not today's deep networks. Statistical models, then what were called kernel machines and kernel-based approaches, and then SVMs, random forests, et cetera, and then deep learning today. The other interesting thing is that actually the models, the rule-based systems or the logic-based systems, were way more interpretable. They could tell you why they made a particular decision, because the inference chain was very explicit. As performance has improved, as recognition errors have gone down, and as computational power has gone up, we've been inventing techniques that are sort of further from the road, if you will, that they sort of give you inferences that are way more accurate, that are way more right on average, but it's very difficult to understand why exactly did they make this particular decision, which has led to this whole area you heard about before about explainable AI or something, saying, but we really need to understand this both in order to improve these systems and in order to protect ourselves from some of the biases or incorrect decisions they might make that might be systematic in some way. A bias, in some sense, is a systematic error, right? It's not random. It's somehow systematically correlated with some attribute or feature of the input population, right? So we'll shift now from saying, okay, that's the context. This is how things evolved. This is sort of how machine learning, which I think has powered AI, and I'm introducing a subtle distinction by saying that between ML and AI, by saying AI is sort of the encapsulation of technologies into a human-like capability, whereas machine learning is something that powers your ability to do that. We'll look at this area of human-computer interaction. Now, HCI itself has sort of advanced in decadal leaps since the 70s. In the 70s, it was character mode interfaces. In the 80s, it was graphical user interfaces. In the 90s, it was the web. All of a sudden, your graphical user interface, which was a great toy to interact with right there and gave you satisfaction, now became a window into the world, with it becoming the web, and that unleashed a whole new set of applications. And then there was the mobile revolution, which basically made that window portable. You could carry that window with you to the rest of the world. And then, in some sense, is the arrival of the voice user interface, which is that's just you. That window, you don't have to carry it with you. You just ask, and the answer comes, right? That's, I think, it's great when you can put up an icon like this, and it conveys a message, which is that you talk to it, and it answers back, right? And so this, we, at least in Amazon, we think about this as the arrival of the ambient computing area, where the computing thing is no longer a tangible thing that you necessarily carry with you, you touch and interact with. But we go back to using that most natural of interaction mechanisms that we're used to, which is voice, and then use language to convey what you want. Right? What are the different, so now, in some sense, a capability like conversational AI or ambient computing sits on top of a number of foundational technologies. So a lot of advances have to be made in different component technologies for you to be able to synthesize a capability out of it. So there's wake word detection, which is how Alexa knows you're talking to her. Second is speech recognition, which is how Alexa knows the exact words you spoke to her. Then there's natural language understanding, which is how Alexa knows what do those words sort of mean? How do I operate on those words? Then there's a bunch of stuff that goes into resolving the logic, et cetera. And then there's text-to-speech, which is the generation of the response to the user saying, yeah, I understand you, and here's what I'm going to do. All of this is in that box that you buy. It's also available as what we call Alexa Voice Service, or AVS, as a SDK for other device manufacturers to onboard onto their devices. And there's more than 150 different third-party devices that actually use Alexa voice services to enable voice interaction with their devices. So an example of how Alexa processes a particular utterance, imagine you just ask Alexa to play Message in a Bottle by Sting. Now you know one of the artists I really like. So first the utterance goes in, ASR recognizes it, the recognition results comes back, and if you're using the Alexa voice service, then this is where you tap into it, and if it is just our own Alexa device, then it just goes straight down this way. The NLU component looks at that recognized speech and says, I see a play directive here to me. I understand that there's a play directive. It also understands that the song name is Message in a Bottle, and the artist name is Sting, because there could be Message in a Bottle songs by other artists there sometimes. So all of this is useful information. It uses that intent in combination with these arguments that we like to call slots or entity values. And then it does two things. One is it sends back a text message, a speech message to the user saying, I'm going to play Message in a Bottle by Sting for you. And it also, there's an application that launches that song so that you're actually enjoying the music. Right. Now, of course, it's great if you can sit back and ask somebody to play you a song and it plays you a song. That's an awesome experience by itself. But our aspiration for Alexa was to be a always there assistant, advisor, question answer for you. And so it's particularly important for us that Alexa becomes more and more competent every day. And over the last 5 years, we've actually achieved that. Alexa now, through both work at Amazon and through the third-party skills developers who develop a lot of skills for Alexa, Alexa now is capable of more than 100,000 different skills. Right? These could range from engaging you in a game of Jeopardy to answering questions like my youngest daughter likes to ask her, what's 50 times 625? And you should go try it. And you can use much larger numbers, and she will still give you the answer. Or what's the capital of a city? Or tell me more about Millard Fillmore, who is one of our presidents. She has to write an essay for her class. So all of this is becoming woven into our lives in a way in which, so my youngest daughter now, who's the most facile user of Alexa in our homes, does her homework at the dining table because that's where we have a screened Alexa device. So she can actually interact with it and learn about the world as she's answering it. And then she'll come and tell me, by the way, Dad, she needs to answer these additional questions too, right? Because they're asking us in school. So, and I actually do take it back and we give it as feedback. All of you are welcome to send us feedback about the things that you want. We actually do process all of that, and we greatly appreciate the time people take in giving us feedback. So it's got 100,000 skills. Now, it's one thing for a device or a capability or an AI or a human to do lots of different things. But it's quite another thing for that same entity to do them all better over time. And so the thing that we're really proud of is the fact that not only is Alexa doing more things, many, many more things than she did every year, each year, year on year. Every year she does those things better, each one of those things better. And these improvements, and now all of you know the answer to this question I'm going to ask. What do you think drives these improvements as a technology? Ease of use is one, thank you. From a technology perspective, deep learning, right? So many, many things about deep learning make it just the amount of data that it's able to consume and it's able to learn without ceilings. There are things like people look at in terms of the capacity of a learning system, et cetera. Turns out deep learning, the deep networks, just have a tremendous capacity to learn and generalize from more and more data, right? That's also the source of some of their fragilities as we look at later. So I've just chosen to highlight a couple of deep learning-driven improvements in Alexa's performance. One is active learning. Some of the researchers here might know, but for the more general audience, active learning is a way of saying, if I have a fixed budget for training data, for learning samples, how do I spend it best to get the most improvement in my system? Put in more simpler terms, if I could collect just one more training sample, what should that one more training sample be, right? So active learning has allowed us to reduce data in some cases by a factor of 40. Yeah, 40. So, which means if something took 1,000 samples to achieve a certain level of performance before, we can do it with 25 samples, right? Or if it was 100 samples, it's roughly 3 samples. You get the same performance. It's not in every case, but those are some of the most impactful cases that we've seen. A second is transfer learning. Transfer learning is where, it's an uneven world. You have a lot of data for some domains. You have a lot of data for some languages. And I'm sure actually the government folks in this audience are very familiar with the notion of how many of the languages outside of English and the Western languages there's very little data and very, very, very sparse linguistic resources available for them. So the question is there a way in which I can take my learning from all of these data-rich domains and languages and use it to somehow improve my performance in data-poor conditions or data-sparse conditions? And transfer learning is a way of addressing that, right? And so we actually have seen major improvements, not as much as with active learning yet, but substantial improvements by using transfer learning. For example, you have domains like weather or restaurants, and they are very data-rich because people use it all the time. And then things like recipes, you're looking up for new recipes. It turns out you can improve your performance in the recipes domain significantly by leveraging what you've learned for weather and restaurants. The same notion of transfer learning applies also for cross-lingual transfer. It seems like a little bit of a stretch, but it works. If you learn certain concepts in one language, like English, you can actually transfer some of that knowledge to German. There was, in one of the slides before, and maybe actually in one of the conversations before, people were talking about embeddings, about a numerical representation of meaning in words, which is sort of something that deep learning has enabled. Turns out you can force embeddings to have the same numerical values across languages, and if you can force it for some words, you can try to force them into the same place for other words. That allows you to transfer information in a very numerical way. For the more technical in the audience here, I'm grossly simplifying it, but I think I got the general concept right. Then we want Alexa to become more natural, right? So back in early 2018, if you wanted Alexa to play Hootie and the Blowfish and also turn on the bedroom lights, you'd have to issue 2 separate commands. Alexa, play Hootie and the Blowfish. Alexa, turn on the bedroom lights. Now, you can just say, Alexa, play Hootie and the Blowfish, and turn on the bedroom lights. And again, the technological infrastructure here is deep learning. It allows us, without any increase or any change to the user in terms of speed, et cetera, to decompose that and to operate on both of those simultaneously because they're, in principle, separate actions being taken by separate devices, and they both happen with just one command. Another practical example of it is for those of you who use Alexa for shopping, you can say, Alexa, add strawberries, peanut butter, bread, bananas, and pasta to my shopping list, and she'll add all of those 5 at the same time. That's a different kind of a complex utterance where you have multiple entities, but it's just one intent. A different kind of context, apologize for the thing here, at least I see that here. So the probabilistic, sometimes you also want, context is super important in being natural. So I ask you, what's the weather in Annapolis today? And you tell me so-and-so. And then I say, what about Boston? Right? Or what about tomorrow? So if I ask you, what about tomorrow, the context is, it's still the same location. It's just I've shifted the temporal context. But just as easily, that other question could have been, what about Boston? In which case, the time is still today. The context I'm carrying over is that the time is today, but the new entity is location. The other part that's implicit here is the second question has nothing about weather, but you still know that the conversation is about weather. Right? These are things that we as humans take for granted. As somebody else was talking about, it's very hard to tell machines what you want and to program them to do what you want. So creating this kind of capability requires a fair amount of research work and science work. I'll give you an example of how.
Alexa, what's the weather like in Cabo San Lucas?
Right now in San Lucas, Mexico, it's 75 degrees Fahrenheit with cloudy skies. Tonight's forecast has clear skies with a low of 69 degrees.
What about tomorrow?
Tomorrow in San Lucas, Mexico, you'll see lots of sun and can expect a high of 82 degrees and a low of 68 degrees.
Mark, we're going to Mexico!
And that's what a lot of you are going to be saying in about a month and a half. So, having lived in the Northeast for 2.5 decades, I know how that goes. So we also want to go beyond speech. So now you have something that can be useful to you in many different ways. So we go beyond speech in the sense that we're looking for acoustic events. So imagine you're leaving your house, and you just say, Alexa, I'm leaving. And you've turned on this feature called Alexa Guard, which is available with all the Alexas out there. But you have to turn it on. And then that automatically activates Alexa Guard. And so now, let's say there's a smoke alarm or the sound of glass breaking. Alexa can send you an alert. And again, all of this, because there's so many different things you might want to do, you want a technology that's fundamentally scalable and can learn to detect all these different sounds without it having to be a different piece of software for all of it. And once again, it turns out that with multitask learning in the context of a deep learning framework, we can do this. Right? Beyond spoken language, this is where we're still acting on the language, but we're acting on just more than just the language. This is what, the tip of this iceberg is the whisper mode. If you whisper to Alexa, she'll whisper back to you. And of all the features that I demo at my home when I have visitors, for some reason, this whisper mode grabs attention the most because there's something about Alexa responding to sort of the way in which something is said rather than what is being said that grabs the imagination. So let me give you a second example.
Oh, rough day. What's for dinner? Shh. Alexa, open Domino's.
Hi, welcome to Domino's. Would you like to place an order or track an order?
That last second is my favorite part of the video, actually. That's why I had them included. I use this video more than I should, but I just love that dynamic that I see. I guess reminds me of myself sometimes. But anyway, there's another thing here about how you can use this for just like things. Earlier today we were talking about, there was some question about how might AI change or like surpass humans, et cetera. And who knows? But what I find much more exciting is how can AI work with humans to help us surpass our own limitations? Because there are lots of complementary capabilities here. And a very simple example of that, most of us forget different things. I often forget where I place different things in a home. You can actually just tell Alexa, every time you put something there that you tend to forget, where you put it, and then you can just ask her, where is the drill package? And she'll tell you, it's in the garage. You can even be more specific. It's in the shelf in the garage, or it's in the left-hand shelf in the garage, etc. Again, we do this using some form of deep learning. Another exciting capability, one of our most recent major technology launches, is self-learning in the field. You deploy a system. We make a promise to our customers. Alexa's always learning. She's always becoming better. And we want her to become better directly from just the feedback that the customer is giving her with no human in the loop. So this self-learning in the field, there's no human in the loop beyond the customer interaction. And this is affecting many, without getting into numbers, tons of utterances every day. So you say something like, Alexa, play Sirius XM Chill. It fails, but then a bunch of different people say it fails, and some of them come back and say, play channel 53. And it turns out you can learn robustly mappings between new concepts. You can both learn them at the shallow end, at the very tip of the spear. You can also bring those concepts back to your system and use them in different contexts. Like if somebody then wants to ask a question about who started something, you should be able to borrow that concept and use it again because now you know what it means. Other example is send me Lopper. You can even learn how your ASR errors might be affecting you and bring that feedback back to improve ASR. Learning to paraphrase, this is yet another thing. There are two questions that sort of mean the same thing. Another example from my machine translation days when I was doing speech-to-speech translation under the DARPA TransStack program was, what is your height and how tall are you? Are really the same question. It's not cool if it works for one thing and doesn't work for the other, so you want the machine to learn paraphrases and be able to respond to both. I'll just skip over this. The key thing for us now with Alexa is there is this notion of the AI stack that's out there in the community. Right? You're moving up from phenomena modeling, which is like modeling speech or language or vision, et cetera. This is speech recognition, object detection, et cetera. You move up the stack to making intelligent decisions. You then move up the stack to being able to reason about things, not just like take input, not just data to decisions, but data to reasoning and decisions. And of course, we do want to get to autonomy, which brings a whole lot of different issues about what does autonomy mean and what are the guardrails you need, et cetera. That's many, 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 many years away in terms of real autonomy, though in the context of self-driving cars, you see one example of autonomy which is very real in the world today. And then what I think of as sort of beyond top of stack, which is this notion of automated general intelligence. I'll give you 2 or 3 examples of Alexa's societal impact. So one is Caden. Caden is a kid who is, I think, maybe 13 or 14 years old, I forget the exact age, unable to talk, able to communicate. And you really should go read the story. If you search for Caden on Google, you'll find it. The interesting thing is he was home alone. His parents had gone off to a movie, and they had somebody watching him, but he was in his room by himself. He was able, because Alexa had learned some of his things, he was actually able to call his grandfather and ask him to come give him a car drive. And this was a transformative moment for the family because this was the first time he had operated independently to actually get his grandfather to come. Could have happened with a variety of different technologies, but the fact that we played a role in some, however small, in something like that is a major booster of our sense of social mission that we're serving. A second example is going back to this Alexa Guard. This is actually a real thing. So this is how you get this thing, and it actually resulted in the thief being caught by the police. It's on Reddit, so you can go take a look at it. It's public. Third real-world example is from India, where I met this teacher last month. I was there in India for the Hindi launch of Alexa. He saw Alexa and he thought this could be a great way of getting his students to learn English. So they have sort of an incentive system. The better a student does, the more questions they get to ask Alexa. And another thing Alexa can do is tell you the spellings of words. So you can go and ask Alexa, how do I spell onomatopoeia? And she will tell you. And so they use things like that to help these students learn English. This teacher started this with investing his own money, him and his partner. And now we have sort of expanded that program to a number of schools in that state, and we'll probably continue expanding that program. These are all, in some sense, creative uses of the technology by the world at large. We did not go and ask somebody to use it in this way. It's just a capability that was put out there, and people started using it in different ways. I'll skip over that in the interest of time. Sort of the last section, the talk. The risks and opportunities of AI in a more general sense. I chose to focus on two things. One is, one risk which I think we need to address collectively is bias in AI systems. And bias comes in many, just like as with humans, bias is insidious. It comes in ways that we don't even know the ways. So we have to discover those things. The second is, you have to start questioning beliefs you've had for a long time fundamentally. Is seeing really believing? And you saw an example of it in this morning's talk. There was one slide. The first one, these word embeddings. One of the most exciting things with this deep learning stuff is we're able to get a numerical representation of meaning. I know it sounds like weird, but you can actually perform an algebra on semantics. So, for example, you can say, take the embedding vector for man, subtract the woman, add uncle, and you get, maybe it's the other way around, and you get aunt, right? It turns out that these equations sort of work, not always, but they sort of get you in the rough ballpark, right? But then, now we can operate on the meanings of words, right? We've solved the problem. This is great. But then, when you look at it in different contexts, for the he column is for the men, and the she column is for the women. Brother, sister, fine, awesome. Beer, cocktail, right? Employment, occupation associated with a man, physician, registered nurse. You heard this from one of the other speakers as well. A professor, this is interesting. It's not just a different thing, it's even rank. Professor and associate professor, right? So there's bias in both visual and language models. So I just showed you the bias in just purely language context. Now let's look at visual context. And this is by Kai-Wei Chang at UCLA, somebody I know, and my PhD student has been working with him as well. And so who's the agent for this image? Obvious answer is it's a man, the kitchen. But just the fact that the visual context was kitchen biased the models towards saying it's actually a woman in the image chopping the vegetables. Not everything, some cases benign, but still sort of indicative of bias. So, of course, though, our standard defense is, but this bias is just in data. The data just represents today's human biases. And that answer is unsatisfying in two ways. One is, it's not particularly satisfying to say the biases have always existed, so we should live with them. Regardless of technology, we want to improve. The second is it true that we're just reflecting the biases in training data? So there were some experiments done again by Kai-Wei. Data set gender bias. So there was this, for this visual context thing, examples, there was 33, 66% bias in that data, gender bias. But the system actually learned a much more amplified version of the bias. Right? So it's not true that these systems are only as good as the data they get. They could sometimes be worse, be more biased. A second risk is, so that's sort of the implicit risk in technology. It's nobody trying to do something bad. It's just how technology is. Second is generative adversarial networks. I won't ask you guys which of these images do you think is not real. I'll just give you the answer. They're all real. They're all generated. None of them is a true picture. This is just there was an article in TheVerge.com that this comes from. Just in the last 3 to 4 years, it's gone from where we were generating rough-looking, avatar-like images to now you can do this, right? Why does this matter in an online world? You could have multiple identities. We're increasing. It'll start becoming increasingly hard to tease apart things. So these are all things that we need to worry about. Turns out the technology for this is pretty easy. A lot of people can go exercise it and create reasonable versions of this, even if they don't get state-of-the-art results. And the fundamental idea is simple. You take a random number, you pick a random number, you have a generator that can operate on that seed and create images. You have a discriminator that simply says real or not, because it knows the answer it generated, and every now and then you give it some real images as well, and it knows the answers. Turns out you do this right, and one of my PhD students has become really adept at doing this right. You can generate real-looking images all day long. Another thing you can do is actually transfer style. These are the images of, the photos of 3 people. These are photos of 5 other people. And imagine you want to generate this person in this style. Here it is. You want to generate this person's photo in this style. Here it is. Entirely automatic. Right? So you can see the risks associated with this kind of seeing. Is seeing really believing? It's hard to get that, right? Image to image, you can do the same. You can transfer Biden's expression to Obama. You can transfer all of these things. There's also, we don't know this all the time, but software being used across the country to predict future criminals. And this software, this is where the bias can become insidious, can be systematic in certain ways. And you can go online and read this article. But in a very practical sense, society, we have to worry about these things, right? There are many, many other risks. I just chose to exemplify a few. You can fake cancer on medical images, discriminate on credit denials. Somebody else mentioned that earlier today. Many, many more things. Sometimes some of these things that you fake can have big societal impact, because imagine that you faked some of your medical data set, and now the government makes a huge investment of taxpayer resources in solving a problem that actually didn't exist because somebody was able to convince people that this is a problem worth solving. And there have been examples outside the US of that, right? But I still believe, started by saying we're technology optimists, I'm a technology optimist. I still believe the biggest risk is actually walking away. So we need to figure out how can we use this technology and use it right. So the last few slides, so doing good with AI. As I pointed out, there are 2 different risks I see. One is where the technology itself has some limitations. And the second is where it can be put to malevolent use because of what it can do, and they need different solutions. But first, doing good with AI, you can actually combat deep fakes with AI as well. There's ongoing projects. There's a DARPA Metaphor project, a follow-on program called Semaphore that's coming up. I was involved in the Metaphor project for the first 2.5 years before I went to industry. And it turns out you can do a pretty good job of detecting deep fakes. This is a little bit, though, like a race, right? Technology is improving. You need to improve your detection thing. So it's not like a solved problem. But you can actually do a pretty good job of detecting fakes. So these are 2 different systems, and you can see that you can do a very good job of detecting fakes. Not a perfect job. You can also say, where did the manipulations happen? Right? So that's something else that allows humans to focus and say, is this really a fake? Second, combating the scourge of human trafficking. One of the other big technologies is the internet, associated with the dark web. People can use the dark web to sell all kinds of services. One of the big things that happens there is human trafficking. It's not difficult to find examples of it, but to string together evidentiary chains that allow law enforcement to get convictions is a really hard problem. And so this was also a DARPA project called MEMEX, and I was involved in the early years of it. My colleagues at USC, Pedro Secli, and others have been working on this. This is just the economics. This is what drives that industry. These are some other stats. It is shocking. I mean, some of you should just go look at some of this data. But once we deployed, but look at this. This thing flourishes because of a lack of investigations and convictions. But once we deployed this AI-based technology, which was really knowledge graphs, stitching together evidentiary chains, and allowing investigators to quickly look at patterns, look at this is from the HTRU in the Manhattan DA's office, Human Trafficking Response Unit. Look at how the number of investigations have skyrocketed. This is what leads to convictions, right? This is an example of the real-world impact. This is real users telling us this is being used. I should skip this like this.
Everybody, this is Dominic Grillo. He's,
I'm the reason you guys are all here. So I couldn't sleep last night, so I ran a MEMEX search on the flagged phone.
Dominic, MEMEX? What's MEMEX?
It's a visual search tool developed by DARPA.
It displays links within criminal enterprises. I've never.
You can get testimonials from the Manhattan DA's office, but you know you've arrived when Chicago PD talks about you, right? So I couldn't resist playing that clip. Many other use cases that are enabled by MEMX. My very last couple of slides. In addition to using AI for good, we also want to develop better and better AI. And we talked about this earlier today, the panelists did. Fairness, I think, in addition to just defining accuracy as a metric, it turns out to be a very challenging task to define fairness as an objective metric to optimize to, but there's work going on there. Transparency, this is about interpretable AI. How do you interpret the decision? How does the AI help you interpret its own operation? Ethical use of AI, I think each of these requires different sort of solutions. The first two are sort of technical or science and research problems. The third is actually a conversation and bringing different disciplines in. When somebody says, what are the biggest risks with it? I was very hesitant to put some risks. There's sort of an ethical aspect to it, and there should be ethicists as part of the conversation or philosophers. So the creation of multidisciplinary forums, which is happening right now across academia. At Amazon, our take on this is simply that we cannot solve all of these problems on our own, though we have important contributions to make. So we're working with multi-sector initiatives like Partnership on AI to stimulate some of these multidisciplinary forums, stimulate this conversation. We're also launching collaborations with academia. Recently, earlier this March, some of you might have noticed the NSF Amazon call for fairness in AI research proposals. That was something that I helped launch. From the Amazon side, we contribute half the funding, NSF does the other half. So with that, I'll just say, when I look forward to a future that has 75 billion connected devices, I think of the power of AI to bring all of those connected devices together in a world that we function in much more effectively, much more securely. And that, I think, is one of the most exciting promises of AI. Thank you.
Professor Natarajan, thank you for that great talk. And we started a few minutes late. We could probably do one or two questions before we have to move on. So if you had anybody who's got a burning question, take to the mic. If you're loud, I'll repeat your question.
You mentioned using machine learning to detect deepfakes and artificially generated text, maybe something like that. What's to stop a malicious actor from taking that and using that as the discriminator in another step of deepfake?
Nothing, really. And that was my point, that this is an ongoing race, that our goal in some of these is to be one step ahead and to have it. And sometimes it's access. So if you looked online, my colleague, Wael Abdelmajid, who's leading this deepfakes project now at USC, since I left it, or since I've left on leave of absence, has just posted a message on LinkedIn and Twitter saying he's not going to share his, even though there's a lot of requests to share, and the practice in the community is to share the code, he's decided to not share the code in the interest of not allowing that kind of. So it's going to change culture too in some ways in order to fight some of this. And some of those cultural changes are not without their negative impacts as well, but so there's a trade-off. But I think it's a constant race. You're going to have to constantly be one step ahead.
Okay, you've got it.
Good afternoon, sir. Could you talk more, I'm Michelin first class year, sorry. Could you talk more about the steps that you're taking to address biases in AI and who makes these decisions?
Okay, did you hear the question clearly?
I think the question was, could you talk more about the bias in AI and who makes the decisions? Is that what you said?
Yes, like we see biases in in the training data, and how do we mitigate that, and who makes the decisions to mitigate this?
So
biases?
I think I'll give you a slightly broader answer, which is, so we know that there are biases in all data, right? And we know that systems today are also biased, even human workflow systems. So we're trying to say, okay, how can machine learning help us improve that situation? And so one of the areas of work that I'm involved in is this thing called invariant representation. So if you take a conservative approach to saying, I'm only going to use the information that's useful for solving this particular prediction task, and I'm going to force my network to not learn things that are not related. So if you take the example of generating speech or generating text, and you say, I don't want gender to be a useful thing in doing it, then I can actually train my network to ignore these sources of biases. So now the question is, who defines all of those biases? That's usually a community effort. So there are people out there who will say, okay, in these tasks, these are the kinds of biases. There are data sets out there that say, this is how. Bias assumes that you have a label for it. That's why it's a bias. It's a named thing. There's a related problem, which is just generally called nuisance, which is there are a bunch of things that actually affect it, that if you put a name on it, it could be biased because it's systematic in some way, you just don't know. And so all of these invariant representation learning things also aim to address nuisance. There are variants of it that address nuisance. So that's sort of the technological solution in terms of how you address this problem. In terms of defining bias and its impact, it's usually a multi-sector initiative defining what are the biases, analyzing them. You'll see a lot of papers on this, for example, from Nicole Lee at the Brookings Institute, et cetera, putting out papers saying these are the different kinds. In the criminal justice system, for example, pretrial detention is often based on a prediction of who's unlikely to show up for trial or less likely to show up for trial. And if you use that for prediction, you might end up detaining them pre-trial so that they show up for the trial, the first day of the trial. But it turns out that the real problem is usually something else, which is either their inability to find childcare or transportation for an elder or something. And so there are better solutions to those problems that come up, and those usually require multiple disciplines to be involved.
Thank you.
If I may ask one question as the moderator, this is it. You said don't give up on AI, and we talked about the risks. One of the things you often hear about Alexa in particular, but there's other examples, but let's talk about Alexa because of your association, is where does that data go, and how can I feel comfortable in my own home with where is all this information going? So what is the answer to that to make people comfortable that this is not in itself a risk?
Yeah, fair question. So a few different things. So I think I've said this a few times to people at my table, like Amazon is a customer-focused company, and customer trust is crucial to us because we know that our ability to operate successfully is based upon the customer trust we earn. So there are things we continue. So first, everything we do is focused on making sure we don't breach that trust. Second, there are technologies or like new features. So for example, this December 25th, Dave Limp, Senior VP for Devices, he's in charge of the entire device organization, announced this new feature. So before, we had this thing where you could go and delete everything you want, or you could keep. So we don't keep anything that customers don't want us to use. They can go delete everything. But to make it easier, because we heard from users, we introduced the auto-delete functionality so that you can now go and say, auto-delete my stuff in certain things. So there are things like that we do. Beyond that, it's how all companies protect data. So I think that's what I can say is the customer is very much in control of their data. It's up to
No, thank you. And thank you, Doctor. This was excellent. And we want to give you a copy of Cyberspace and Peace and War from Mike Levicki. But thank you very much.
Thank you. Thank you all.